Thanks so much for having me. So I'm going to talk about software for quantum machine learning. I'm going to take a much more high level approach. I assume, hopefully, I'm right that most of the audience has good experience and grasp of regular classical machine learning, but maybe not so much for the quantum. So I'm going to try to kind of bring those two worlds together and give you a high level overview. If you thought 6 qubits wasn't very much from the last talk, well, I only have 1 qubit in my talk, so get ready. First, I just want to give you a little introduction to the company I work for, Xanadu. We're a Toronto-based startup. We were founded in 2016, so we're about 4 years old now. Offices are right downtown Toronto, actually on the 29th floor. It's a really nice view from there. We started with 10 people and have grown now to over, I think, 60, maybe even 70 now. We're growing at a real rapid clip. It's quite something to see. A lot of technical people, as you can imagine, with PhDs from all over the world, but not just in quantum. We have people on the software development side as well, algorithms research, a broad spectrum of technical people at our company. We're venture capital backed, with the majority of our funding coming from Canadian sources, which is actually something we're pretty proud of. We raised $45 million in 2019. So, we like to consider ourselves a full stack quantum computing company, and this is because we're building both photonic quantum computing hardware as well as quantum software. So on the hardware side, we currently have and are continuing to iterate on our sort of what we would call our noisy near-term Gaussian boson sampling device, while we're simultaneously developing new devices so that we can achieve universal fault-tolerant quantum computing, sort of like the Holy Grail of quantum computing that everybody's going after. And on the software side, there's a few things that we're working on, but our primary focus is a software package called Pennylane. So Pennylane is a quantum machine learning software library for Python that allows you to connect your favorite machine learning libraries like TensorFlow or PyTorch to various quantum computers from different hardware providers. And you can run quantum machine learning algorithms on those hardware devices. So to motivate why you might want to develop a quantum machine learning software library, we can take a look at some of the things that have made deep learning so successful over the past maybe 5 years now. So in the case of deep learning, hardware advancements like the developments of GPUs really helped propel the field forward because of the reduction in costs associated with training algorithms on something like a GPU. If anyone's ever tried to train a deep neural net on a CPU, you know all about this. Also workhorse algorithms. By workhorse algorithms, I really mean backpropagation. The backprop algorithm that lets you train deep neural networks efficiently. And finally, having the development of user-friendly software that's specialized for the purpose of building and training neural networks for rapid prototyping that enables researchers and practitioners to really propel the field of deep learning forward. It's been a huge contributor to the success in the deep learning field. So just as a reminder, as a primer for everybody, the deep learning workflow follows sort of these standard steps, right? So first you would define your neural network, which is just a mathematical model or a function, really with some free parameters. Next, you would specify a cost function that's going to link the performance of your model to some training targets. Then you're going to train your model on those targets using something like gradient descent, where the parameters of your model are going to be updated in the direction of steepest descent, the parameter landscape relative to your cost function. You're trying to minimize that cost, and you're trying to iterate over these parameters such that you can get to the minimum possible cost for your model. And then finally, you hope your model should converge on a local or hopefully a global minimum in this parameter landscape. And now you can take those trained weights, that trained model, and you can perform inference on some unknown targets. So this workflow is great, but really, why should we limit ourselves to training like a neural network or a machine learning model? The concepts of differentiable programming, which grew out of deep learning, take that idea, right, the concepts of deep learning and that workflow, and really says that you can apply those concepts to train any code or function that has parameters. And so, what does that look like? Well, the main difference, with deep learning is that rather than training a model in the form of a neural network, you would have, with differentiable programming, a classical function or a mathematical function. But this doesn't have to be a model for differentiable programming. Right? This could be something like a graphics engine, for example. So you see this little animated peace sign here. So you could train all sorts of pieces of code, but you would use the exact same techniques as you would for machine learning to train them. So there currently exist several software libraries on the classical compute side for differentiable programming. This isn't a brand new concept. I mean, in the early days of TensorFlow, you couldn't use Python for and while loops or if statements, for example, but now most of these libraries let you mix Python code with mathematical operations. So they're approaching that differentiable programming paradigm. The key features, of course, of these libraries is the automatic differentiation, which means that the calculation of the gradients that you need to access in order to train and update your model is taken care of for you in a seamless and transparent way by this software toolkit. Now, right now, the environment around quantum machine learning is starting to look a lot like it did back when deep learning started to really take off and have huge success. So, we have new quantum processors rapidly being developed and that are being made to be available to people everywhere in the world over the last few years via various cloud platforms like Xanadu and IBM's. And many of the workhorse algorithms as well from deep learning, gradient descent basically, can be basically directly copied and applied over to quantum systems quite easily. We'll go over that in a little bit. And finally, this sort of third pillar that we talked about for deep learning, we're seeing this as well for quantum machine learning. There's an emerging software space for quantum machine learning right now. So, like as I mentioned already, at Xanadu, we're developing Pennylane, but we're not the only player in this game. There's also TensorFlow Quantum, also Tequila from the University of Toronto, to just name a couple. So there are various frameworks that are starting to come out to facilitate this rapid development and prototyping of quantum machine learning algorithms. So now, sort of, this is the the $1 billion question. So we need to talk: how does quantum machine learning software work? So we want to use the same ideas as deep learning to make quantum machine learning software. So how are we going to do that? Well, the key idea is to start with a quantum circuit. So, a quantum circuit is made up of a sequence of gates that are parameterized. So these gates will manipulate your qubits based on the parameters associated with that gate. And then the parameters for your gate elements, these are going to be the free parameters of your model. And then finally, so you're going to run, right, your parameterized circuit, generate some outputs that you can measure, and then this will be what you'll use to then feedback to tweak those gate parameters to rerun to make a new measurement. For example, it's really all about these parameters that are associated with the gates that manipulate your qubits. So I don't want to go too deeply into the details here, but the key point and the main takeaway from this is just, as I was just saying, that this output from running your circuit, this B on the left here, it's linearly dependent on the gate parameters. So this, on the right here, you've just got this measurement of you're taking an expectation value of some measurement quantity B. You're running your circuit. You'll get a lot of different answers, but they will, you can take an average over these to get some value, an expectation value for that B. And those parameters of those transformations for those gates depend, or let's say the intractable function that's doing this manipulation depends linearly on those parameters. So, for example, like the psi here and the u's, these are just vectors and matrices. So every step is just linear algebra, just like with deep learning. It's all linear, so you can absolutely train this thing. So because the outputs are depending continuously on those gate parameters, the gate parameters are candidates for optimization by a differentiable programming. So what this means is we can treat a quantum circuit like a complicated black box, but a black box nonetheless, where we feed in some data and parameters, and we get out a mapping of that data and parameters to some value. And then since this black box is differentiable, we can use the same tools as in deep learning to train this process. Now, of course, like most things, this is a bit of a simplification. The devil is in the details, and here the details really are the I mean, the key feature of machine learning, and it's how do you compute the gradient of a classically intractable function. So luckily, there is a trick that works for efficiently computing the gradient of a quantum circuit, and this is called the parameter shift rule. So the parameter shift rule says that we can get the gradient of the function that our circuit is implementing by evaluating our circuit with a slightly forward shifted value for the parameters and then a slightly backward shifted value for the parameters and taking the resulting difference from those outputs. It doesn't work for all possible gates, but this is a general rule. So you might be familiar with something like the finite difference method for getting gradients. This is not the finite difference method. This is actually a macroscopic shift where you're shifting these gate parameters by a macroscopic large amount, recalculating the outputs. But the intuition is kind of the same. It's just this is a special thing that works for quantum circuits doing these shifts. So now that we have all those pieces, we can kind of put them together, right? We need to create multiple circuits, ones that are shifted, because you can't peek at your circuit while you're running this. So you have to create your shifted circuits to run in parallel, but you can create those with the shifted parameters, calculate our gradients, we get our gradients, and then we've got all the pieces that we need to basically iterate on the training workflow there. Now, this whole routine has a name. It's actually called variational quantum circuit. So you might run into that in the literature. And this is really the sort of first class of algorithms that you're likely to encounter when you're learning about or implementing quantum machine learning especially on today's hardware, our noisy intermediate hardware. It would be a variational quantum circuit. These types of circuits also can be known as a hybrid quantum classical model. You'll see that as well, or just called hybrid model, because you're putting in classical data, you're doing some quantum computation with that data, you're measuring out again a classical output at some physical measurement, performing the optimization step using some classical algorithm or computation like gradient descent and repeating. So often these things are called hybrid models. But really, like this first step, this variational quantum circuit is just the first tier of hybrid algorithms. I mean, you can think of much more complex architectures, of course, by allowing the classical model that you're using for optimization to also be trainable. Why not, right? And then you start entering this realm of sort of arbitrary hybrid quantum classical models, where you take a trainable quantum circuit, you take a trainable classical model, you could build, one that feeds into the other, that then feeds into another, and you can have these end-to-end trainable hybrid models that incorporate both quantum and classical components. If you've ever used something like TensorBoard, you might be familiar with images like the one on the right here that's showing a computational graph. So a computational graph maps out all the steps in your machine learning model to a graph, where really each node of that graph represents a function that's being applied to your data, and the flow of data through those functions, the input, the output relationships between them, are represented by the edges of that graph. So to build quantum machine learning software, you can take this idea of a computational graph and extend it by replacing some of those classical nodes in the graph, but with quantum circuits, this Q node. The idea, this black box that we talked about, right? So we call these Q nodes. So you might see this come up a lot. A quantum node or a Q node is this idea, this self-contained differentiable quantum circuit. So in a larger model, some piece of work is handed off to a quantum computer, which might do some processing, hands its result back off to the larger model, much like you might hand off processing to a GPU, for example. The other piece that you need to train this in the hybrid model, of course, you got to compute the gradients using your parameter shift that we talked about. But really, we've covered all of the pieces that we need here to put it together. You can and do this, right? So, I guess more specifically on the software side, though, if you want to be technically, how are we going to do this, right? You might take something like your tensor object. You would then take it from TensorFlow or even a NumPy array, strip away all that class structure because you don't want any of that stuff. Then you want to feed that data in so that your quantum node understands it. And then, of course, when it comes back out, you just rewrap it the same in the same wrapping that it was coming in with, and you can feed it down on the line. So it's really not too difficult to integrate one of these Q nodes or something into that sort of network. As I mentioned, just like sending data to a GPU for special processing, you could do the same thing with these Q nodes, and everything can be abstracted away because the unwrapping and wrapping of these particular data formats is something you want your software to basically handle for you. So this was a big high-level overview. I think it would be a good idea to maybe go through an example and see what this looks like. So as I mentioned, my company develops Pennylane. So of course we're going to use Pennylane to do this. So this is just the plug section for Pennylane. It's an open source Python library. It's completely free and open source. Lets you connect the classical and quantum resources together to make these hybrid quantum machine learning models. I strongly encourage you to check out the GitHub page and the website for Pennylane, pennylane.ai. It's really, really great. There are tons of demos and tutorials for QML. These are just Jupyter notebooks that you can work through on your own. Installing it is as simple as pip install Pennylane, and you're up and running right away. You can use the simulator backend locally to work on this. You don't need to connect to hardware to get going, and it's great. The team is really great. I think they spend a lot of time trying to make things as accessible as possible. And it's also, because it's open source, you can contribute back too. If you have come up with a fun demo or something interesting, absolutely open a PR and submit it. We'd love to see that. So we're going to be using Pennylane, and we're going to be doing this is sort of a standard kind of hello world type program for quantum machine learning, where we're going to start with a single quantum bit, a single qubit, and it's going to be in a particular state, which is shown here on the block sphere. The block sphere is a standard way to show qubit states. So the red arrow in the sphere on the left is the starting state for this qubit. It's pointing up in the positive Z direction on this block sphere. And then we're going to train a circuit to take that qubit, and by applying two rotations, a rotation about the x-axis, a rotation about the y-axis, it's going to manipulate that quantum state so that it ends up pointing in the negative Z direction, that sphere on the right, where the red arrow is pointing down, without specifying what those angles should be. So you see in the middle of this slide, at the left, we have our initial vacuum state pointing in the Z direction. We're then going to pass it through two rotation gates, RY, with free parameters for those rotation values. Then we're going to measure the output of whether it's pointing up or down. We're going to want it to point down. So if it's pointing up, give it a big penalty, try it again, and then train it to figure out what do I need to do with these parameters so that I can get that output pointing down. So what does this look like in code? So of course, to get started, you need to import the Pennylane library. Since there are so many functions and methods from the library that we're going to be using, it's always a good idea to sort of import it as a shorthand, something like import Pennylane as QML, for example, the same way you might import NumPy as NP. And then in this example, we'll use Torch for our machine learning library, so I also want to import that. So after importing our libraries, really the first step is you want to tell the software which quantum device you want to use. So in this example, we're using Rigetti's Forest QPU. So this is an actual quantum processing device offered by Rigetti that Pennylane will plug into for you if you have an account. If you don't, you can use a simulator. But you could use Xanadu's photonic computers as the backend for this, or simulator as you like. So this is kind of like if you're telling TensorFlow that you're going to be using CUDA to connect to a GPU, the same idea here. You want to specify what device you're going to be using for this computation. So then after we've specified that device, we're going to need to define our quantum computation in the form of a circuit. So you heard a little bit about this last talk, and then I also in the last few slides had this circuit depiction of how we're going to be manipulating that qubit. So we have to specify that circuit in code. So our circuit is parameterized by two rotation angles, that phi1 and phi2. And these are going to be arguments to our circuit function. And we're going to apply them to the rotation about that x-axis, rotation about the y-axis for the block sphere. And then read out the resulting state. So, so another distinction is that in quantum circuits, we refer to qubits as wires. So you'll see this a lot because they're circuits. So we look at a qubit as a wire in the circuit. This is why we define wires. We have one qubit, so we're manipulating wire 0, counting from 0. And then, okay, yeah, finally, the last step here is we are going to be, sorry, it's too small. Yeah, returning the expectation value, right? So that, as I mentioned, that's that measurement, the B in the brackets, measuring that expectation value of the position of this qubit, and then using this as the output for measurement. Right, and then the last piece, right, the Q node decorator. So we need to indicate that we want this circuit to be run on a quantum computer. So we need to use this Q node decorator, quantum node, to indicate that we want this circuit to be run on the device that we defined above. And there is a typo in this, I apologize, in that definition, that Q node definition, it shouldn't say dev, it should say QPU. So we're indicating that we want to run on QPU, not that we defined just above, not dev. Sorry about that. Okay, and then so that's setting up our circuit. Once we've done that, I mean, there's a bunch more code, but this is actually all just should be fairly familiar to you if you've worked with Torch. So this is just classical optimization at this point, right? You'll recognize this as defining our cost function, defining our parameters, making them trainable, choosing an optimizer, training the circuit. Here we're using 300 steps, and that's all we need at that point. So really, just that first piece of defining our circuit and indicating that this is going to be our Q node is all you need to set up your quantum circuit. The rest is Torch code. Okay, so then what does this look like? So when we run this, you'll see the sphere up in the top right is actually an animation of what's going to happen as you step through these different parameters. So it starts here, when it goes back there, it'll start at the top at the red X, and then what we do is to make this animation more interesting, actually partway through training, we switch the target. So it's forced to change direction, but the X is the red X is the target. And then that arrow is then the result as the parameters train and as it finds that target. And then we just switch the target to make it keep going and go look at the next one. In the bottom right, you can actually see a picture of the optimization landscape as you run through this, through these steps. And that's it. And there you have it. You can run this on your code or on your laptop tonight in about 10 minutes if you'd like. So these capabilities that we just talked about, this is compatible with pretty much any machine learning library. Like we use Torch here, but if a machine learning library has broad enough feature set that lets you define custom devices and gradients, so like NumPy, PyTorch, TensorFlow, like how they do, then you can work with that framework with Pennylane. And then, for example, you can see here where I've just, taken the toy example we just went through in PyTorch and converted it to NumPy. There's very little difference, right? On the right, you're using a simulator device rather than the forced QPU. But if you ignore that little minor difference, you'll see that the circuit setup and definition is the same, with the only difference being that boilerplate for each of these. This is just more plugging for Pennylane and QML. Again, please go to the Pennylane website and check it out. Tons of great tutorials in a lot of different applications, QML applications that you can explore there as well.
At the start of your talk, Paul, you mentioned something about the Holy Grail in kind of quantum computing and quantum technology that everybody's going after. Please elaborate.
Sure. So quantum computers are a little bit different than classical computers. I mean, obviously, but there's also another distinction to make. So right now, the quantum computers that we have that are real, that exist, that you can use right now, are called noisy intermediate scale quantum devices. This is because they lack error correction. They lack any ability to recover from corruptions that happen during the calculation. So you have to do your calculations quickly, right, before sort of noise takes over. Where people are going, most quantum computing companies, not all, but most, are towards a universal fault-tolerant quantum computer. So this is a quantum computer where you can correct for those errors, so that if something happens, that you can recover that information. effectively. And it's not until we get there that we're going to see quantum computers do things like crack all encryption that we currently have, or these kind of claims that people make for quantum computers being super powerful. You have to get to that point. There will be points along the way where quantum computers will be able to do things, I don't want to say maybe not better, but maybe specific problems that a specific architecture of a quantum computer can do more efficiently than a classical computer. But it won't be universal. It won't be able to do anything. But basically, once you hit this level of you have enough qubits and they're fault tolerant and you can correct for them, you could simulate with that quantum computer any classical computer. So you'll have a crazy powerful quantum computer. Of course, there's always going to be realistic sort of trade-offs to how much does it cost to run this thing. I don't think classical computers are going away by any stretch. There's going to be just like the QPU hasn't made the CPU obsolete. There's absolutely going to exist this hybrid sort of infrastructure where specific tasks that make sense you can offload to a quantum processor, whereas other ones it makes perfect sense to keep running with a classical computer, for example.
From what I've seen, a lot of these biotech drug discovery companies aren't really paying attention too much in regards to their teams on quantum computing. So what I want to do is kind of understand quantum computing is its own kind of space here, drug discoveries here. What needs to happen for quantum computing to kind of break through into the mainstream and become more accessible for companies like that?
A lot of it is about education, right? It's about us, the practitioners, getting out there and saying, "Hey, look, you can do this type of thing with this hardware," right? It's a big challenge right now for a company, even one that is looking to the next advance in computing, to know what they can do with it. It's a challenge. I totally get that. So I think it's really up to us to seek out those use cases and then bring them forward and really promote them and let them know that it's there, that they can, that this capability does exist, and that they can tackle it. Yeah.
At the moment, for now, quantum computing is still very much on the fringes, you know what I mean? CTOs, CIOs haven't even got there yet, you know what I mean? They're still wrapping their head around what they can solve with traditional computing, and quantum is just, as I said, it's so next level for so many people and a lot of businesses. It does seem like, like light speed, like how do we get there? We can go very far and do a lot of things with light speed technology, but we're not there yet. So I think it's going to be really interesting next few years. I love this space. I love all this fringe technology. Since all we are doing is calculating gradients and updating parameters, why is it so hard to train a quantum model?
It's not so hard to train a quantum model.
Well,
the big challenges right now are just the depth of the circuits, right? You just don't have enough qubits to do anything that you can't do classically. So once, I think we heard about this a little bit in the last talk. There are no quantum machine learning algorithms that are outperforming classical because they just don't have that capacity yet. I think one place that they're going to really is with those kernel methods. I mean, with the embeddings, because you're embedding into this infinite dimensional Hilbert space, you sort of get separation between classes for free in that embedding. There's been some early indications that might be really a strength for quantum machine learning, but it is still early days for that.
Are you doing research and generating new algorithms or implementing reported algorithms? We can expect a limitation due to the lack of algorithms, or shouldn't we worry about that?
It's still wide open. So the QML field is very young, and I think there's still lots of space for even just blatantly porting ideas over from classical machine learning and deep learning into QML. You'll probably see, if you check out the applications page on the Pennylane website, most of them are deep learning, straight out of deep learning, but with a quantum twist, for example, right? There's like doubly stochastic gradient descent, where just instead of just stochastically sampling mini batches, you're also stochastically, I think you're, what are they doing in terms of the updating parameters, right? So this sort of like little tweaks coming from there. I think this is the reason I think that we like to do these kind of events as well, is to really reach out to the machine learning community and AI community, because you find that people that are trained on quantum tend to have a very different mindset when they look at machine learning AI versus those who have a background in machine learning AI that come to quantum. And it's those people, the machine learning and AI background people, to come over to quantum that then start seeing these connections of, wait, we can do this, we can enhance this AI algorithm or a machine learning algorithm this way with quantum, whereas it seems to be slower the other way around. So we really like connecting with ML and AI people and getting them familiar with quantum machine learning to start to get away maybe into more unique territory of what can QML do.
Are there any resources or extracurricular learning opportunities for high school children to learn the basics of quantum computing?
Yeah, there absolutely are. I was just talking with a group the other day out of they're in BC. They're doing a bunch of outreach. I'll see if I can find the name of the initiative. I can never remember it. But yeah, there are a lot of groups actually doing outreach for high school. I mean, at first you kind of joke and think, well, I mean, a high school student, do they really need to know about quantum computing? But if you think about it, if we're sort of projected to get to the scale that we need to for universal fault tolerant quantum computing in the next 5 years, they're graduating and they're going through undergrad and they're ready for grad school. They're ready for jobs. Like, you need to start training them now to be able to work with this technology. So it is out there. Let me know, connect with me, and I'll try to find the name of some of those initiatives.
What's the business model for Pennylane? Open source software is free training. Where is the money coming from?
No money, just giving back to the community. Yeah, it really is. I mean, it actually grew out of how to say, like a project of love, really. So Nathan Killeran, who started it, he had a background actually in quantum computing. Then he went and did a postdoc in AI machine learning. Again, saw seeing these connections, seeing the interest there, realizing that we're on the cusp kind of having all these things line up for quantum machine learning, and just decided this is something that the community needs and that we need to be researching. Again, to move that field forward, you need to provide those tools to people. So really, from like a researcher at heart, this is what we need as a community. So we're going to build it. And if we're building it, then we can build it right. And if you're building something for profit, not always, but often there can be compromises, right, around usability. But free open source tools are great because everybody gets to contribute. People get to see the flaws and call them out and fix them. So yeah, there is no Xanadu as a company. We're venture backed. We hope to one day maybe make revenue, but that's maybe on the hardware side, on the services side in terms of our cloud offerings. But for the software like Pennylane, that's a labor of love.
Is the main expense keeping quantum hardware near absolute zero in temperature?
It's a great question. Again, it varies. There are so many different architectures to say what is the primary expense. It definitely depends, but it is a big challenge for superconducting approaches to keep everything at superconducting temperatures. It's one aspect that actually makes our hardware really appealing. So we use photonics, it's just light, and we operate at room temperature. We don't have significant losses at room temperature. So that's really nice. Actually, you can all of our hardware, we're actually in an office building on the 29th floor, and our lab is in the office, just in the office, right? Our hardware sits in a server rack, co-located with a bunch of other just standard IT stuff. No cooling required, which is a big benefit for us. Other costs, of course, but cooling is not a cost. Just like any new technology that you're developing, there's huge R&D costs, right? And scaling up technologies, it costs a lot of money. Usually, salaries just for the people as well, right? It's not a massive field. There's not as many specialists out there. That's really, and the cost. A lot of the cost really is from that R&D and that iteration, right? To get things, and as you scale, you run into new problems you have to tackle as well. So that's really where that's universal. Those are the costs for everybody, right? One thing that's really nice though is that actually the cost of actually running a quantum computer can be quite low, especially if you don't ignore cooling. But like the electricity costs are low. So in fact, once so at a device like ours, if you're at the scale where in the next few years where we can start to tackle problems that you can't tackle classically, the electricity cost of running that computer is much cheaper than running a classical computer to do the same. So I know that this has come up a lot in these days with these crazy figures coming out about how much it costs to train, something like these language models using GPUs and just the crazy expense. But so that's one thing actually where quantum does promise. There's those sunk costs of R&D, but after that, then things actually get a lot cheaper.
Do other people have a future in quantum hardware after the Chinese group's Qi Zhang came out? Are there any authority figures in the QML field in academia?
Yeah, absolutely. People have a future in quantum hardware. Again, there's many different approaches, right? And none has been obviously, in my opinion, all of this is my opinion, I would say, no one architecture has demonstrated that this is the one that's going to make it. Nobody else will, right? So things are still wide open. In terms of authority figures in the QML field in academia, again, biased here, but I would say Maria Schuld. She is affiliated with Xanadu and Pennylane, but she's also a researcher in the University of, I'm going to mispronounce it, so I'll probably just post it in the chat afterwards, but she's a professor in quantum machine learning in South Africa, and she's fantastic. I mean, if you've never seen one of Maria's talks, I strongly recommend it. There's a few on our Xanadu YouTube channel. You can also find them scattered around various channels where she's given talks. They're fantastic. And she'll be speaking at QHack as well, which is free, totally open to anybody to participate. We're going to be streaming it on Twitch. You just got to pop in and you can watch all those talks.